నమస్కారం అండి శ్రీనివాస్ గారు. మీ మాట వినిపించట్లేదు. మీరు ఆడియో ఆన్ చేయాలి. అన్మ్యూట్ చేసుకోండి.
అన్మ్యూట్ చేయండి ప్రొఫెసర్ శ్రీనివాస్.
Okay. Now, am I audible, sir?
ఇప్పుడు వినిపిస్తుంది.
Hello.
హలో హలో ఇప్పుడు
Am I audible, sir?
ఆడిబుల్.
Okay, thank you. So, we are very fortunate, sir, that you have accepted to deliver a lecture to our students and us, right?
Thank you very much, sir.
And Professor Ramanamurthy JV is very well known to us and is a friend of us. He is an eminent teacher and he is a famous researcher. I think he produced around 8 PhDs. And we are very fortunate, sir, to listen to your lecture. We welcome you. And I'm sure our students do benefit from your lecture, and we too do benefit. And I wish you happy presentation, sir. Please go ahead.
Thank you, sir.
శరణ్య,
ఇది స్క్రీన్ షేర్ అవ్వట్లేదండి.
గుడ్ మార్నింగ్. ఆన్లైన్ ఉన్నావా కాలేజీలో? ఒకసారి మన వాళ్ళందరికీ కూడా ఆన్లైన్ లో ఒకసారి జాయిన్ అవ్వమని చెప్పవా? జస్ట్ ఫర్ ద నంబర్ స్విప్.
Is my presentation screen is visible? Hello. ఇది ఒక్కసారి చూడు శ్రీనివాస్, మీకు తెలుసా నరేషన్? ఈజ్ మై స్క్రీన్ విజిబుల్ సార్? Am I audible? Audible, sir. Screen is not. Screen scare అవ్వట్లేదు.
Yes, sir. It is visible.
Screen is visible?
Yes, sir.
Okay. జూమ్ వస్తుంది. ఇది ఎట్లాగా? అది మళ్ళీ ఈమెయిల్ ఇవ్వాలా? మళ్ళీ అడుగుతోంది ఇది. మేడం, ఎవరండి? నాది స్క్రీన్ షేర్ అవుతున్నట్టు నాకు కనిపించట్లేదు. హలో, ఇక్కడ మళ్ళీ ఇది జూమ్.
Screen is visible, sir. Screen is visible.
Is my screen visible?
Yes, sir. Visible, sir.
This slide is visible, huh?
Yes, sir.
Yeah, finite difference methods of partial difference equation.
Then I can present. Okay.
Yes, sir.
Yes, sir.
Pretty shared.
Okay. Shall I start?
శ్రీదేవి, Madam.
Okay, start, Amma.
Yeah, madam. Sir? Sir, welcome address అయిన తర్వాత స్క్రీన్ షేర్ చేద్దురు గాని సార్.
Okay.
I will request you, sir, to share the screen later, sir, after completing the welcome address. Okay, sir. Okay, sir. Thank you. Madam, shall I start, madam?
Yes, Sridevi, you can start.
Respected our Honorable Vice Chancellor, Professor Sita Ramarao Garu, Director Academic Professor Sudharani Garu, Registrar Dr. A.V.N. Reddy Garu, Dean Faculty of Sciences, Professor Pushpa Chakrapani Garu, and all the faculty members, counselors, and dear students, a very good morning to one and all. Dr. B.R. Ambedkar Open University is celebrating its 40th anniversary. On this occasion, the Department of Mathematics is organizing its first webinar through online. Today's webinar is on finite difference methods to PDE. I extend a warm welcome to all the attendees for this program. I am thankful to our Vice Chancellor, Director Academic, Dean Faculty of Sciences for extending their support and encouragement to conduct these webinars. Now, I welcome Professor Pushpa Chakrapani Garu, Dean Faculty of Sciences, who is the guest of honor of today's program. I welcome you, madam.
Yeah, thank you, Sridevi.
I also welcome speaker of today's program, Professor J.V. Ramanamurthy Garu, Professor, Department of Mathematics, NIT Warangal. Welcome you, sir.
Thank you very much. Thank you. Very good morning to you all.
Thank you, sir, for accepting our invitation. Now, I request Professor Pushpa Chakrapani Garu to say a few words about the webinar.
Respected Vice Chancellor, Professor Sita Ramarao Garu, Registrar A.V.N. Reddy Garu, Director Academic Professor Sudharani, Sridevi, please request the admin to unmute, to mute all the participants. Today's speaker, Professor Ramanamurthy Garu, NIT Warangal, and Professor V. Srinivas, Head Department of Mathematics, Dr. BRAOU, and Dr. Sridevi, and all my dear fellow colleagues, participants, and my dear students. Very good morning to all of you. I also once again welcome you all for this webinar. Sir, you know, Dr. B.R. Ambedkar Open University is the first open university in India. And as Sridevi said, we are celebrating our 40th years of our establishment of this university. In this connection, all the faculty members are come up with different programs like webinars, seminars, workshops in different ways, in different subjects by all the faculty members. So in this, as a part of that, Department of Mathematics has come up with the webinar series, and this is the first webinar from the Department of Mathematics. I congratulate the Mathematics Department, particularly Dr. Sridevi, who is the webinar coordinator for initiating this type of programs. At the outset, I would like to thank our speaker today, Professor J.V. Ramanamurthy Garu, NIT Warangal. Sir, thank you so much for accepting our invitation and to deliver a lecture on finite difference methods to PDE. So definitely with your rich experience, this program will be definitely very much useful to our students as well as the other students and other participants who are joining in the webinar. And since I am not that much familiar with the mathematics, I'm not from the mathematics department, I don't want to take too much time. Thank you, Sridevi, and congratulations once again. Thank you very much, Professor Ramanamurthy Garu, for accepting the invitation to deliver a lecture today. Thank you one and all.
Thank you, madam, for your valuable information about the webinar which we are conducting. Right now, I request Professor Srinivas Garu, Head Department of Mathematics, to say a few words about the webinar.
Respect.
Sir, unmute చేసుకోవాలి mic.
I did it, sir. Respected. I did it, sir. I hope I am audible.
Yeah.
Now
Yes.
audible.
Audible, sir.
Respected Vice Chancellor, sir. Respected Director Academic. Respected Dean. Mr. Registrar. The other deans and respected directors and friends. We are very fortunate to have Professor Josila V. Ramanamurthy Garu with us to deliver a lecture on finite difference methods to PDEs. Our students are very lucky to have you here, sir, from a reputed institute, and you are a good friend of ours, and you are well known for your expertise as a great teacher, and you have produced around 8 PhDs. You are a great researcher, and we are very lucky and fortunate to have you here, sir. I welcome you into this lecture. Please go ahead, sir. Thank you.
Okay, thank you.
Yeah, just a minute, sir. Dr. Sridevi, I request you before starting the lecture today, I request you to please introduce today's speaker to our audience and as well as our students. Thank you.
Thank you, sir, Srinivas, sir, and thank you, madam. Now I am going to introduce our speaker. It is my privilege to introduce our speaker of today's webinar, Professor J.V. Ramanamurthy Garu, who is going to talk about the topic finite difference methods to PDE. Professor J.V. Ramanamurthy Garu was born on 9th July 1961. He did his MSc and PhD in mathematics at NIT Warangal. He joined as assistant professor in 1993 at NIT Warangal. In his career, Professor Murthy Garu worked as head department of mathematics during 2014 to 16 and dean students welfare during 2019 to 2021. He served as counselor in CCB unit for AIEEE admissions at NIT Warangal and also served as program officer at Vinikicherla in AP government program Janmabhoomi for development of rural areas. According to his research contribution, the areas of specialization are non-Newtonian fluid flows, micropolar and coupled stress fluids, homotopy analysis method, mass and heat transfer. Professor Murthy Garu published 92 research articles. He guided 8 PhD students and 41 MSc dissertations. He reviewed various research journals. He is the life member of Indian Society of Technical Education, Andhra Pradesh Society of Mathematical Sciences, Indian Society of Theoretical and Applied Mechanics, National Academy of Sciences, and also he is the life member of Administrative Staff College of India. Professor Ramanamurthy Garu received an award, Outstanding Presentation, for a paper presentation at HEFA, Orlando, USA in 2014. He also received NCC and Guard of Honor Award in 1980 by President of India and also by Dr. Neelam Sanjeev Reddy Garu. Once again, I welcome you, sir. Now I request Professor Murthy Garu to start his presentation.
Thank you very much. I thank the organizers. Sabha Saraswati Namaha. Very good morning to all the participants here. The Vice Chancellor of the University, and Dean Faculty, Professor Pushpa Garu, and the Head of the Department, Professor V. Srinivas Garu, Sudha Rani, and the present coordinator for this session, Dr. Sridevi Garu, and all participants. It is an opportunity given to me to present myself before you. And in the topic, I required to present the topic in such a way that it should not be a mere classroom teaching. giving the example and solving it like that. So it is a test for me. So I took it as a little bit theoretical oriented. At the same time, they should have a formula for that to use, and why this formula is useful. Like that, I want to develop. So I will first share the screen. Today's topic is finite. Is my screen visible to you all?
Yes, sir.
Okay. Today's topic I choose as the finite difference method to partial differential equations. Initially, I thought of presenting all types of partial differential equations and their finite difference formula, but it will be very difficult to present all topics in a single 1 hour class. So I confined to only diffusion equation. The diffusion equation, we call it as a parabolic equation, and its analytical solution for a simple case we have taken, and its forward finite difference scheme is developed. And then the error analysis, what is the error involved in this scheme, that is shown. And then for the stability of this partial differential equation in the numerical scheme, there is analysis called error analysis by Fourier method that is also taken. And then unconditionally stable formula we want to derive. For that, we will take implicit scheme. These are the topics for parabolic equation we want to take. Now, parabolic equation, a general case, one-dimensional case, we can take in the equation 1. This is U is a heat source, let us say, heat quantity or temperature. Then dou U by dou T is equal to dou by dou X of B dou U by dou X plus C into U plus D. This is the one-dimensional heat equation where U represents the temperature, and it requires, this is a first order differential equation in T. Therefore, in T we require one condition. That condition at T is equal to 0. In general, we specify that condition, we call it as initial condition, and it is involving second order derivatives with respect to X, with respect to space. Therefore, with respect to space, we require two conditions in X. These conditions are called boundary conditions. We are specifying them at two different points. A standard interval, we take it as X is equal to 0 and X is equal to 1. Therefore, at X is equal to 0 and X is equal to 1, we have to specify the boundary conditions. Now, this equation 1 without these conditions is not complete physically to solve. Therefore, at T is equal to 0, we have an initial condition U x comma 0 is equal to U naught. And at X is equal to 0, at one end of the bar, we have a mixed boundary condition. This is alpha U plus alpha 1 dou U by dou X is equal to alpha 2. And at the other end, X is equal to 1, we have beta naught U plus B1 dou U by dou X is equal to beta 2. These are the boundary conditions. These boundary conditions are restricted by some conditions in order to have a solution. These conditions are alpha naught and is positive, alpha 1 is negative, but alpha naught minus alpha 1 is positive. And again, at the second end, we should have beta naught greater than 0, B1 greater than 0, beta naught, beta 1 greater than 0. And the sum of these coefficients is also greater than 0. This is, if these first two conditions are mentioned, beta naught plus B1 greater than 0 is automatic. These are the conditions required in order to have a solution. Now, for this equation 1, we want to take a simple special case. This equation 1 represents heat flow in an inhomogeneous medium with a source included, and medium is having different properties at different values of x. So we have Bx. Now we will take homogeneous medium, then B1, B becomes 1 and source is 0. Therefore we have C and D are also made 0. And with homogeneous boundary conditions, we call them as Dirichlet boundary conditions. Then the very simplest case for equation 1, we can have equation 4. This reads as dou u by dou t is dou xx, that means the second derivative with respect to x, for t greater than 0 and x is in between 0 and 1. This is subject to the boundary conditions. For t greater than 0, u of at x is equal to 0 must be equal to u of 1 at t must be 0. This condition is equal to 0 is necessary. These conditions are called homogeneous conditions. These homogeneous conditions we can introduce to have a separable variable method. If the homogeneous conditions are not present, then we cannot take a separable solution. So for separable solution, if you want to have, these homogeneous conditions are necessary. Again, initial condition ux comma 0 is equal to u naught. This is for x is in between 0 and 1. Again, to have a solution, possible solution, you should expect in terms of t a continuous solution. That means if you have continuous solution, this initial boundary condition u naught x must satisfy the boundary conditions given in x. That means at x is equal to 0 and x is equal to 1, we should have 0. That means u naught of 0 is equal to u naught of 1 is equal to 0, you should have. Then you can have a continuous solution in terms of t. Otherwise, this solution will not be a continuous solution. A discrete condition will be imposed, even though we are not telling here, this is a physical boundary conditions required to solve the partial differential equation of parabolic type. This equation we call it as diffusion equation, and energy equation we call, and we call mathematically as parabolic equation. Now, this equation 4 you can solve by separating the variables method. Then we can have a solution like this. Ux comma t is infinite summation am e power minus m pi square t sin m pi x. This is the solution. This solution is a right solution. You can check. For example, if you put x is equal to 0, sin 0 is 0, therefore u0 is 0 at x is equal to 0. Similarly, if you put x is equal to 1, sin m pi we have, sin m pi is 0, therefore u of 1 comma t is 0. Then you put t is equal to 0, initial condition we have. Then we have summation am sin m pi x is equal to u naught x. Then u naught x is a known function. Then we can obtain the value of am by integrating by using half range sine series. Then the solution is complete. Here I have not evaluated the value of am. I have just given the solution, how it is obtained. But if you find am, then the solution is complete, and this solution is rapidly converging. Why rapidly converging? We have e power minus m pi square t. If you put t is equal to small value, then even if you increase t as a small amount, then e power minus m pi square will be a big value, and therefore e power minus we have. Therefore, it will reduce to 0 very quickly. Therefore, in this summation, we need not take many terms. If you take finite number of terms, then you will get the solution, and you need not have infinite terms here. That is the solution, nature of the solution. But there is a limitation for this solution. What is this limitation? This solution we cannot generalize easily even for a slight modification in the equation. That means what is the equation we have? This is the equation. Ut is equal to uxx. But if you take b is also included, you can write ut is equal to b uxx. Even for this, the method of solution, if you take here, this solution you cannot generalize. Just b you cannot introduce here in equation 5. Therefore, this is the limitation for this method. Even a small generalization, slightest modification if you make, you have to make the nature of the solution to change so much. So therefore, this method of separation of variables is having this limitation. Now, our aim is, since we have seen the solution you can represent in terms of finite number of terms, you can assume that this solution we can take in finite difference methods, and by taking finite number of terms, you can have a solution approximately equal to the actual solution. That is the assumption. So we take mesh points like this, 0 to 1, we divide into mj plus 1, capital J plus 1, number of grid points in x direction, and in t direction, we take infinite points because t is having infinite interval. The solution is valid for infinite values of t. Therefore, we take n is 0, 1, 2, 3 up to infinite values. The solution is valid, we take, but we stop at a particular value of n, and we will get the solution up to that value of n. You can have solution for parabolic equation. Now let us assume delta x, the step length is uniform, and it is 1 by j. J is the number of intervals here. It is starting from 0, ending with capital J. Therefore, the number of intervals are number of mesh points plus 1, number of mesh points minus 1. Number of mesh points are j plus 1. Therefore, number of intervals are j plus 1 minus 1, that is j. Therefore, interval length is 1 by j. This is the interval length, uniform interval. And you assume u at xj and tn is represented by un j. This is approximate solution for the actual solution u x comma t. Now, this equation right hand side, this right hand side ut we have, you replace ut by a finite forward difference formula in time, and central difference formula for space uxx. Uxx you replace by finite difference formula, central difference formula, and ut you replace by finite forward difference formula. Then here, dou v by dou t, you can represent it as v at tn plus 1 minus v at tn by change in the time. Similarly, dou square v by dou x square, a general second order central difference formula, you can have v at tn minus 2v at tn, v at j plus 1 minus v at xj plus v at xj minus 1 by delta x square. This formula 7 we substitute in equation 1, equation 4. If you substitute in equation 4 and rearrange the terms, then we can have uj at n plus 1th time is equal to this n term you take to the right hand side, and therefore we have u at n plus 1 time is u at n plus mu times uj plus 1 minus uj plus uj minus 1. This is the second order finite difference, and where mu we can write it as delta t by delta x square. This is non-dimensional quantity because the coefficient here we have dou u by dou x square. We are representing it as 1. Though it is 1, it has dimensions of conductivity. Therefore, delta T by that conductivity into delta x square will be a non-dimensional quantity. Mu we have. We define it as mu. And for what values of mu, this scheme is convergent. That is our aim to study. So this we call it as a stencil. You take it as the, we have 4 points, j plus 1, j minus 1, and n. So this is at midpoint, this is j comma n, and this upper point we call it as j n plus 1 point. U is evaluated at this point. Therefore, the value of temperature at this above point is sum of these lower points and plus jn we have. So this is the initial condition. This equation we can solve at the initial condition. Uj n is equal to 0 is u naught, and at j is equal to 0 at any time we have boundary conditions, and therefore this is capital J, u capital J n is equal to 0. These are the boundary conditions, and this is the initial condition. Therefore, this difference equations we can solve by using this initial condition and this boundary condition. We assume that at the corners, the boundary solution is consistent. This is what we have guessed in the initial stage. I have explained you. So therefore, at the corners, this value and this value must be same and is equal to 0 as in the initial condition, boundary conditions. Boundary conditions, we have u naught at uj is equal to 0. These conditions must be satisfied for the initial boundary condition also in order to get a solution which is continuous with respect to time. Therefore, these corner points j naught is equal to 0 and j is equal to capital J. These corner points also must have a homogeneous condition in nature. That means the boundary solution must be consistent with the corners. This is the assumption we have. This assumption is a physically very, very necessary condition. Otherwise, our solution will not be consistent and the solution will be discontinuous with respect to time. Therefore, that is not the nature of the solution which we have seen by equation 5. In equation 5, we can assume that t is continuous and x is also continuous. That nature will not be followed if you don't put here 0. In this equation below 9, 8, you call it as, let us say, 9. If you don't have 0 here, this solution will not be a continuous solution. Therefore, in order to have a continuous solution, we should have a solution like this. Okay. Now, this solution, which we have represented in 8, we compute. So, if you compute, you have to define u naught x. U naught x is the initial condition. You take the initial condition at t is equal to 0 such that the corner points are continuous or consistent. So, you are defining u naught x as 2x when x is in between 0 and 1, and 2 minus 2x if x is in between half and 1. So at 0, you can see that u is 0, u naught x is 0. At 1, 2 minus 2, we have 0. That means the corner points condition, continuity condition is satisfied. For this initial condition, you take j is 20. That means 20 intervals we have considered. And delta x is 1 by j, that means 0.05. This is delta x. And delta t, you take it as 0.0012. And you take another solution by prescribing j as 20 and delta x as 0.05, but delta t is 0.0013. So the solution here in the first case, when delta t is 0.0012 and delta t is 0.0013, what do you expect? The solution must be same, because in delta t the variation is very, very negligible. but you can notice that the behavior of the solution is quite different. Though the delta t value is changed to a very little extent in the fourth decimal place, but the solution changes very rapidly in the behavior. Now you can see here delta t, we have placed the solution like this. Initially at t is equal to 0, the solution is representing two straight lines meeting at x is equal to half. So at x is equal to half, these two straight lines are meeting. This is the initial solution for capital U. And similarly, you take delta t is 0.0013. Then also you can have initial solution is satisfied. So at t is equal to 0, the solution for the first case and for the second case, you don't find any difficulty because they must satisfy the initial conditions. Therefore, both the solutions are same. Now you take t is equal to 1 time step length. If you take 1 time step length, delta t is equal to t is equal to 1, then you can obtain a solution like this, just like a trapezium. In both the cases, you don't find any difference between the solutions. But if you take 25 iterations, 25 time steps, now you can find a small difference in the behavior of the solution. In the first case, the solution is a parabola type solution. But the second case, it is also a parabola type, but at the top points, there is some vibrations you can say. Now, if you go for 50 iterations, taking n is equal to 50, then you can observe that the solution in the first case is continuous. There are no aberrations. But in the second case, there are quite number of aberrations from the actual solution. So you can see a solution is oscillating solution about the actual solution. So this is solution is oscillating about the actual solution. So this behavior we are getting. Why this behavior you are getting? This is the question. Now, if this is the behavior, how can we trust the equation which we have developed? We have developed a numerical scheme and we are expecting that it will behave very well. We have taken delta t 0.012 and delta t 0.0013. We should not expect a perfectly different variations, but you are getting this. Why you are getting like this? This we want to explore. To explore this, you define a truncation error. Truncation error means you are taking infinite series in the U, let us say. You stop at the nth term and you take it as the solution. Therefore, there is an error in the solution. That error, we call it as a truncation error. So you take capital T is the truncation error. We have taken the equation as ut minus uxx is equal to 0. Now substitute the approximate solution. What is the approximate solution? Plus t means delta of plus t means we are using forward difference scheme. And del square x means here we are taking central difference scheme. Therefore, for the forward difference divided by delta t represents dou u by dou t, and delta square x by delta x square will represent dou square u by dou x square. So this is the truncation error. So if the truncation error is what happening for the truncation error we want to see. So in the first term of the truncation term, delta plus t, you can define it as u at t plus 1, t plus delta t minus u at x comma t. So you expand this in infinite Taylor series, and the first term will be getting cancelled. Only from second term onwards, you can have a solution. This solution is ut delta t plus half utt delta square plus 1 by 6 u triple derivative delta cube t. Okay, now the second term we expand. Delta square t in the second term in the numerator is nothing but u evaluated at x plus h comma t minus u 2u my plus u x plus h, x minus h. So these three terms we have to expand in infinite Taylor series, and some terms will be getting cancelled. And the first term here is in u x plus h, first term is u of h. And the first term here is u of x. Here first term is u of x. So u of x is 2ux and minus 2ux will get cancelled. And the first term in delta t is dou u by dou x into h. Here minus dou u by dou x into h. So these two terms will get cancelled, and only del square term, del square x term will remain. Similarly, del cube, delta x cube term will also get cancelled. Therefore, del square u is represented in terms of del square x plus del square x to the power 4. Therefore, this is the equation we have. You divide this by delta x square, then the truncation error now is given by capital T is equal to ut minus uxx plus half of u double derivative delta t minus 1 by 12 u fourth derivative delta x square and so on. Now the differential equation is satisfying ut is equal to uxx. Therefore, this term, first term will be dropped out, and then we have the second term and the third term, and higher order terms in delta x and delta t square, like that we have. Now assume the maximum error in calculating the u to t is capital M tt, let us assume, and the maximum error in calculating fourth derivative of u is capital M xxxx we are writing, or you can write m1 and m2. M1 is the maximum error in calculating u to t, and m2 is or uxxxx we call is the maximum error or maximum bound in calculating fourth derivative of u. Therefore, the maximum error, if you want to calculate modulus of t, is less than or equal to half m1 delta t plus 1 by 12 m2 delta x square we have. Delta x square we have. Now you take delta t common, then we have mtt plus 1 by 6 mu m2 let us say. Delta x square, delta t by delta x square, we called it previously as mu. Therefore, this term will be 1 by 6 mu, and m1 plus 1 by 6 mu m2 we have. Now, because u to t is uxxxx we have, this is the differential equation because of ut is equal to uxx. Therefore, if you take once more derivative, you have to take 2 times derivative again on the right hand side. Therefore, we have u to t is equal to uxxxx we have. Therefore, m1 is equal to m2 for all points of x and t. Therefore, if you take mtt common or uxxx common, then this you can represent the truncation error, maximum truncation error. You can represent it as half of 1 minus 6 mu uxxxx or m2 you call delta t. Therefore, if you mu is equal to 1 by 6, then this equation will vanish. This term delta t will vanish, and truncation error will be of order of delta t square. Therefore, for a particular value of mu is equal to 1 by 6, the solution will be converging rapidly, and the solution error, truncation error will be of order delta t square. If you choose mu other than 1 by 6, maybe greater than 1 by 6 or maybe less than 1 by 6, then there is an error here. It is not equal to 0 multiplied by delta t. Therefore, our solution is correct only up to delta t terms only. Therefore, your solution behavior will change. So therefore, we should have a scheme. The scheme is convergent fastly if you choose mu is equal to 1 by 6. That is what we have taken in the previous case by taking delta t is equal to 0.0012. If you take delta t is equal to 0.0013, mu is not equal to 1 by 6. Therefore, there is an error. Therefore, that error is first order error in delta t, but it is not second order error in delta t. Therefore, our solution is varying very rapidly. So, now you can see that the solution is fast converging when you take mu is equal to 1 by 6. This solution, if you want to generalize for the case ut is equal to b into uxx, then delta t you have to define at each point. Every point you have to define differently delta t. So it is very difficult for us to prescribe. Therefore, mu also is difficult for us to prescribe. So mu is equal to 1 by 6 is not valid in that case. That means a generalization for this mu is equal to 1 by 6 is not valid. Is not valid. So here T upper bound in the truncation error J and N, let us suppose. Therefore, modulus of T N comma J is less than capital T, and therefore error in the solution, you suppose it as E. Then E at T is equal to Tn, X is equal to Xj. Then error at that point is defined as U n comma j minus u evaluated exact solution evaluated at xj tn. This is the error in the solution. This is the truncation error. Truncation error capital error is less than the bound of the error. Okay. Therefore, you can observe that this you substitute in the given equation, subtract one from the other, then you can expect a solution in the error at each point, n comma j point. Therefore, you have E n plus 1 is equal to En plus mu del square En minus Tn delta T you have. Or here you can now suppose delta square x you expand, then you can get all the terms in terms of the error evaluated at j, j plus 1 and j minus 1. All these terms you can write like this. Now if you take mu is less than half, then all the coefficients in the error add up to 1. Here 1 minus 2 mu and mu. So therefore 1 minus 2 mu plus 2 mu, or it is 1. Therefore sum of the coefficients in the error is equal to 1. Therefore error in the maximum error, if you call it as capital E, then maximum error is capital E n plus 1 is less than or equal to all this. That is error at the nth stage multiplied by maximum truncation error multiplied by delta T. Therefore, if En is less than 1, you can see clearly that the maximum error is less than delta T, and solution is convergent. Now, therefore, we can write maximum error at n plus 1th stage is less than maximum error at nth stage plus truncation error multiplied by delta T. Now, you can see from the boundary conditions, U0 at T is equal to 0, E of 0 is 0 because the solution must satisfy the given initial conditions. Therefore, error in the solution is 0 at the initial stage. Therefore, E0 is 0, and therefore E1 you can obtain it as as n is increasing, we can have the solution is convergent, and therefore you can write En is less than or equal to n delta t. You can have. Therefore, the solution is convergent if n is less than half. Therefore, if mu is less than half, our scheme which we have proposed is convergent up to the order delta t. If you want a solution more convergent region, if you want to have more faster region, fast convergence, if you want, you have to take mu is equal to 1 by 6. So 1 by 6 is less than 1 by 12. That you can see clearly. Therefore, if mu is less than half, you can have a solution converging up to the order delta t. But if mu is equal to 1 by 6, the solution is convergent up to the order delta square t. This is the error analysis we have taken. Now, there is another way of conducting error analysis. This we call it as Fourier analysis of the error. Now, previously we have seen what is the solution. The solution is by separation of variables e power minus k square t we have multiplied by sin mx. Okay, this is sin mx you can write in terms of exponential function. Therefore, you have e power ik j delta x. And for j, previously we have taken k, and here we have j. And the function of t, you call it as lambda to the power n. And if you suppose like this lambda, we call it as magnitude or magnitude of the mode of the Fourier mode we call. Fourier mode, we have magnitude of the Fourier mode. That is, we call it as lambda. Therefore, at n, un at t is equal to n, we take it as lambda power n multiplied by sin mt we can, or we call it as convert into exponential function e power ik. X is replaced by j delta x. So here, this equation gives immediately a solution in terms of capital U is given by this. U at n plus 1th stage is lambda times un. This equation you substitute in the original scheme, and you can get un as a common factor on. So that you divide un, you divide entirely in the scheme we have. Then we can obtain lambda is function of k is 1 plus mu e power ik delta x minus 2 plus e power minus ik delta x. So here, these two terms, exponential terms, you can combine together, and you can write it as 2 times cos kx, k delta x. Therefore, here we have 2 common. So therefore, we have minus 2 mu, 1 minus cos k delta x. This again you can simplify. You can write in terms of sin square half k delta x. Therefore, lambda, we call it as magnification factor of the mode. So lambda is given by 1 minus 4 mu sin square 1 by k delta x. If you take k is equal to m pi, you can see that here un is lambda power n multiplied by e power this. So this is, you can write like this. Therefore, the error un term, if you take all the terms in the solution for different values of j, you can have a solution like this. Now here, there is a peculiar thing to observe. That is that if you take lambda k and e power minus k square delta t, they are behaving in similar manner. This is one important thing to observe. So you take e power minus k square delta t, expand in the infinite series. That infinite series is given by this. And lambda k, if you take in the above equation, 1 minus 4 mu sin square half k delta x if you take, you can have lambda k is like this. Sine square x, you expand in the infinite terms and simplify. So if you simplify, now you can see the difference between lambda k and e power minus k delta t. These first two terms are same, therefore they will get cancelled. And k power 4 delta t square you can take common, and the other factor you call it as a c mu. Now if mu is less than half, then you can see that this is error. Lambda k minus e power minus k delta t is less than this, or the scheme is convergent for up to the order delta square t. Therefore, our scheme is convergent if mu is less than 1 by 2. This is Fourier way of analyzing the error. And we have two methods we have taken. One is directly analyzing the truncation error and error in the solution. And the second one is amplitude of the mode of the error you can take and analyze what is the amplitude, how maximum the amplitude of the mode is varying. That also will define the error in the solution. Therefore, both ways we have concluded the same thing. Mu is less than half. Therefore, the solution is convergent. Now, here the solution is convergent, all right. But here in this explicit scheme, delta t is less than half delta x square. So here this is a very, very serious restriction. Restriction means you cannot take delta t very large. You have to take delta t very, very small quantities. Therefore, it requires many time steps to get a required accurate solution. And moreover, delta x also we have to reduce similarly. Therefore, there is two restrictions. Delta t we have to take small, and delta x also we have to take very, very small. Therefore, this is a serious restriction. We want to pass over this restriction. Is there any way? Then instead of previously we have taken time forward difference. Now you take backward time difference. And uxx, you evaluated that t is equal to n plus 1. When delta t is small, whether the derivative is at t is n plus 1 or whether the derivative is at t is n, both will be same. Therefore, you evaluate the right hand side at t is n plus 1, and the left hand side you evaluate dou u by dou t by using backward finite difference in time. Therefore, you have un plus 1 is coming in all four terms and un is coming in one term. Therefore, this one term, un term, you take to the right hand side and simplify the equation. Then this equation you can obtain. Therefore, you have mu, u evaluated at j minus 1 plus 2 plus mu, u evaluated at j minus mu, u evaluated at j plus 1. All these terms are evaluated at t is equal to n plus 1. And the right hand side we have ujn. Therefore, starting with j is equal to 0, u0j is known. Therefore, this right hand side is known when we start the solution. And u1 you are calculating, u1 is known now. Now, if you take n is equal to 1, then u of 2 you have. That is right hand side you have u1, that is known. Therefore, in this way we can substitute for different values of n and we can obtain the solution. Now you can see clearly that instead of mu and 2 mu plus j and mu, you call them as a, b, c, and right hand side dj you call. Then you can see that these equations can be put in the matrix form with a tridiagonal matrix. A tridiagonal matrix, right hand side is known with u0 is 0 and u0 is 0. This you can solve by Thomas algorithm. Starting with n is equal to 0, you can compute dj for all values of n, and for every stage of n, you have a tridiagonal system. We can solve them by Thomas algorithm, ultimately the solution is known. Now you can see that here the middle term is more than the sum of the other two ends. Therefore, B is greater than C plus C, A plus C. That means this is a diagonally dominant tridiagonal matrix. Therefore, iteratively, if you say the solution is convergent very fast. Okay, Thomas algorithm, you don't require the diagonal dominance property because it is a system of equations you are solving. Therefore, anyway, you will get a solution. But if you see in terms of iterations, for iterations, Gauss-Seidel method requires diagonal dominance property. Therefore, this matrix is having diagonal dominancy. Therefore, solution is obtained very rapidly. Therefore, implicit scheme will work without any condition on mu. Now, that also you can see. Now, you take Fourier analysis. If you take Fourier analysis, lambda power n multiplied by e power ik delta x we have assumed this solution previously, that you substitute in the original scheme. In the original scheme, it's this equation. This equation you substitute, that formula you substitute in this equation and cancel un zeta. Then we will be getting a solution, an equation in terms of lambda and mu like this. And this you can simplify. And this is the equation we have. Therefore, here 1 minus lambda is 4 mu lambda like this we have. Therefore, you can take lambda common. And lambda is 1 by 1 plus 4 mu and sine square this term. Therefore, for any value of mu positive, this lambda is less than 1 and it is more than 0. Therefore, lambda is in between 0 and 1. Therefore, when lambda is less than 1, lambda power n we are having at the nth stage of the solution. That means this is going to 0. Therefore, the solution at the nth stage is going to 0. Therefore, this scheme is convergent for all values of mu. Therefore, this solution or scheme previously which you have defined is unconditionally stable. Okay. Therefore, instead of going for parabolic equations by taking forward time difference, and though the scheme appears to be first order time convergent, but many times it will not give a computationally convenient solution because it requires more number of steps with respect to delta t and with respect to delta x. Therefore, for solving the parabolic equations, we go for implicit scheme where it is unconditionally stable. Okay. I stop here, and the references for this equation, for this preparation is Numerical Solution of Partial Differential Equations, an Introduction by Martin and Meyers. This is Cambridge publication in 2005. And this book is written very nicely. And here, this book is mainly containing a theoretical orientation and nice introduction and a nice problem presentation is discussed in this book. Therefore, I followed this book. Thank you very much. Thank you for your patient listening. If you have any questions.
Sir, with your permission, students will interact with you, sir.
Okay.
If they have doubts. If you have any doubts, students, you can interact with the sir to clarify your doubts, please. Anybody? Unmute and you can interact with sir. First of all, you have to unmute.
Hello, ma'am. Hello, sir.
Namaste.
Sir, yes, sir. In the last slides, you said unconditionally stable. That part is not clear, sir.
Unconditionally stable with respect to mu. On mu, you need not restrict any condition. For all values of mu, you can see that the amplitude lambda is less than 1. And the solution is represented in terms of lambda power n. Therefore, if the iteration is increasing, lambda value, lambda power n is decreasing. Therefore, the solution is convergent.
Right. As in this, okay. Right, sir. So this is in contrast with the previous method where mu has to be less than half. Is that correct?
Right. This is in contrast with that. That's why we don't suggest forward time difference scheme. Though it is explicit scheme, but it is not fast converging. So implicit scheme, which we have developed in the last, that is unconditionally stable and fast converging.
Right, sir. So in the previous method, in the forward difference method itself, when we wrote the truncation formula for TXT, there was a 1 minus 1 by 6 mu term in it. And you said that whenever mu is 1 by 6, that term will go away and truncation order will be delta t square.
But that is a very, very critical situation. You don't take generally mu is 1 by 6. You should have a range for that. Exactly mu is equal to 1 by 6, then only you will be having delta square convergence, second order convergence in T.
Sir, so my doubt here is,
first order convergence you require, then mu must be less than half.
Right, sir.
The solution will be oscillating about the actual solution.
I agree, sir. But in general, it is better to have second order convergence, right? It will converge much faster.
Then
so
you have to select mu is equal to 1 by 6. There is no range.
Right,
exactly mu must be 1 by 6.
Right, sir. If 1 minus 1 by 6 mu is negative, if mu is greater than 1 by 6.
Whether positive or negative, it doesn't matter. If mu is not equal to 1 by 6, definitely there is an error and you will get solution oscillations.
All right, sir. Okay, thank you, sir.
Okay, thank you. Thank you very much for your interest.
Anybody? If you have any doubt, you can clarify your doubt with sir, or you can put message in chat box also. First of all, you have to unmute and you can put the message in chat box also. You can ask sir to clarify your doubts. Anybody?
అంత కఠినంగా ఉంటే ఎట్లా మేడం? నేను ఖచ్చితంగా వచ్చి సంతకమే పెట్టాలి అని అంటే కష్టం కదా మేడం. నేను వచ్చినప్పుడేమో ఆయన లేడు, సంతకం పెడదామంటే మరి చెప్పు ఎంత తిట్టుకున్నాడో ఆయన.
Madam, please mute Ishashri.
రావాలంటే లేకపోతే 4 వేలు వేస్ట్ అయితే 4 వేలు కట్ చేస్తాను మేడం.
Sir, please share.
Yes. Sir, please mute, all of you, please mute.
మరి ఇక్కడ చూసినప్పుడే నాకు చెప్పొచ్చు కదా, అవన్నీ రాసుకోలేదా? ఇక్కడ చూసే ఆయన పంపిస్తారో, సంతకాలన్నీ చూసారో పంపిస్తారో, మరి ఈయన సంతకం లేకుండా ఆయన వరకు ఎందుకు పంపించారు?
Okay, sir.
Hello, madam. Good afternoon, madam.
Hello. Yes. Any more? Any one of you?
Madam, this is Dr. Ashok from Palamur University, madam.
Yeah. Your voice is not audible clearly.
Okay. No, I have unmuted. Sridevi madam has contacted me regularly and she was taking much care in presentation of this, and I thank the organizers, director of the institute, vice chancellor of the Open University and head of the department, Professor Srinivas Garu, dean students, Professor Prashma madam, and head of the department, and Sri Sudharani Madam and Sri Devi Madam.
Sir.
I thank all the participants for their keen interest and patience.
Now, sir.
Madam.
Continue, sir.
I pay.
Okay, sir. Now I am going to vote of thanks. Good afternoon to everyone. First of all, I would like to thank to our speaker, Professor J.V. Ramanamurthy Garu, for his wonderful presentation. And definitely this is very useful lecture. I hope all the students are benefited by this webinar on this topic, finite difference methods to PDE. Sir, we require your services in coming days. I hope you will extend your services in future to share your knowledge and your views for us, sir. Thank you, sir, for sharing your valuable time with us. And
thank you.
Once again, thank you very much, sir, for accepting our invitation. I would like to thank to our Dean, Professor Pushpa Chakrapani Garu, who is guest of honor of today's program, for supporting to conduct this webinar and inspiring us with your words. I thank all the participants for making this webinar success. Thank you very much. Thank you, one and all.
Thank you, madam.
Thank you, sir.
Thank you for everybody for their patient listening. I stop my presentation. I hope
yes, sir,
this
yes,
interaction will continue. Thank you very much.
Okay, sir.
I am leaving.
Yes, sir. Yes, sir.
Thank you.